Now we will take a look at what is called a telescoping sum. A telescoping sum is written as the formula here: summation from n equals 0 to r of the difference of a to the n could be equal to delta a0 plus delta a1 plus delta a2 until delta ar. If we expand each term here, we will get a1 minus a0, which is delta a0. You take the second term minus the first term, a1 minus a0. Delta a1 is a2 minus a1. Delta a2 is a3 minus a2, and so on until ar plus 1 minus ar. If we flip those terms one on the other, we will get negative a0 plus a1, negative a1 plus a2, negative a2 plus a3, and so on. We can see that a1 will cancel out with the negative a1, a2 will cancel out with the negative a2, a3 will cancel out with the negative a3 until we cancel out all these terms except ar plus 1. So we get ar plus 1 minus a0, the last and the first term. ar plus 1 minus a0. This formula will be very helpful to us. We can rewrite this formula by shifting the index. If we say r new equals to r plus 1, this means r equal r new minus 1. This means the summation goes from 0 to r new minus 1 of delta an equals ar new minus a0. This is just a change of variables which are the same thing, but the change of the index only. We'll now take a look at the telescoping series and the powerful of discrete calculus in that. When we get the summation of n, this formula gives us that if we have the summation of a difference, we can get the output of it by computing the anti-difference of this function and compute it at ar minus a0. We only compute it at two positions, the last and the first one, and we subtract them from each other. So in order to do this, we will have summation of n equals to summation of n to the 1th power, or summation of n to the falling 1 power, which is equal to, we need to find the anti-difference. The anti-difference of this is n to the falling 2 divided by 2. Why? Because we know the difference of n to the falling 2 is 2n to the falling 1, and the 2 will cancel out with the 2, and we left with n to the falling 1, which is the same as n to the first power. By computing it as this term, we can use the formula we derived here to write the summation as n to the falling 2 divided by 2 evaluated at r plus 1 and 0, which is, we know that n to the falling 2 is equal to n multiplied by n minus 1, which is n multiplied by n minus 1 over 2, evaluated at r plus 1 and 0. We will get r multiplied by r plus 1 divided by 2, which is the formula we know we have derived from discrete calculus. To further understand what we have done in the first example, we will take a look at a second example for summation as n squared. Summation of n squared is we can get n to the falling 2 equals to n multiplied by n minus 1. What we are doing here, we want to change what is inside the summation to the falling powers of it, because we know how to anti-different anti-difference of the falling power, because we will increase the falling power by 1 and divide by the new power. So we want to change n squared into the falling power of it. How can we do this? We have n to the falling 2 equals to n multiplied by n minus 1, which is equal to n squared minus n. We know that we need n squared minus n. N here we can replace it with n to the falling 1. When we take n to the falling 2 equal n squared minus n to the falling 1, we can get n to the falling 1 here to the left side. We will get n squared equals to n to the falling 2 plus n to the falling 1. So we can change n squared here to n to the falling 2 plus n to the falling 1. And we know how to anti-difference these functions. We increase the power by 1 and divide by this power. N to the falling 3 divided by 3 plus n to the falling 2 divided by 2, which is anti-difference of this delta. And we know the summation of the delta can be evaluated at the boundaries from 0 to r plus 1 into the following 3 divided by 3 plus into the following 2 divided by 2. Into the following 3 is n multiplied by n minus 1 multiplied by n minus 2, which is the start here with is n, and the number of terms is 3 because we have falling 3. If we do this, we will get the formula r multiplied by r plus 1 multiplied by 2r plus 1 divided by 6, which is the formula we know in the tables. At this point, we can see that the derivative of the powers can be of x to the r is r x to the r minus 1. This is the derivative. And x to the falling r, the difference is r x to the falling r minus 1. We can introduce an operator called phi, which is going to be to change the powers of x into the falling powers of x, which means we can take x to the r. When we apply phi to it, we will get x to the falling r. The difference is r x to the falling r minus 1. Or we can differentiate it first. X to the r will be r x to the r minus 1, and then take the phi. These are equivalent operators, which means if we take d first, differentiate it first, then take the phi, is the same as taking the phi first, then taking the difference. These are the same thing. We can't divide by phi because phi is on the left side and phi here is on the right side, so we can't divide it with each other. Likewise, we can say that the inverse of the difference is the summation, and the inverse of the derivative is the integral. So summation or then we when we take phi, when we take when we take integral, then phi is the same as taking phi, then taking the summation. We can multiply by phi inverse to get the summation equals to phi inverse. Now we will take a look at how to compute phi. Phi is very easy. If we compute phi x, we what we do is we change the power of x into the falling power. So phi x is x to the falling 1. Phi x squared is x to the falling 2. If we want to write it as the powers itself, the original powers itself, we use the definition of the falling power, which is x multiplied by x minus 1 gives us x squared minus x. Phi of x to the 3 is x to the falling 3, which is x multiplied by x minus 1 multiplied by x minus 2. If we open the bracket and multiply each term by each other, x cubed minus 3x squared plus 2x. This is how we can compute phi. By computing phi inverse is a little bit trickier. Phi inverse of x equals to phi inverse can operate only on the falling power. It don't know how to deal with the original power. So we want to change the original power into the falling power. X to the 1 is the same as x to the falling 1. And when we get the falling powers applied to it phi inverse, we change the falling power into the original powers as it is. So phi inverse of x to the falling 1 is x. We'll take a look at the second example. Phi inverse of x squared is phi inverse of x squared is the same as x to the falling 2 plus x to the falling 1. We have derived it before. When we have falling powers, all of the terms are falling powers, we can apply phi inverse easily by changing the falling powers into the powers itself. X squared plus x to the 1. X to the 1 is the x, so x squared plus x. Phi inverse of x cubed can be derived uh, as previously as we have did here. Let me show you. N to the falling 2 is n multiplied by n minus 1. We distribute the terms and we will get n squared equals n to the falling 2 minus n plus n to the falling 1. If we need n to the falling 3, we will open the brackets and collect the like terms and then evaluate n to the falling 3 as the falling bars of it. Why we have introduced phi to work as the powers of polynomials? Is it a good reason? Is there a good reason for this? Yes, because all functions can be written out as a polynomial series. Like if we need to get the phi of e to the x, we will review some algebra before this. We know the polynomial series for a plus b to the x is the summation of r equals 0 to infinity to x choose r, a to the r, b to the x minus r, b to the x minus r. X choose r, it is x to the falling r divided by r factorial. This is from the polynomial series. E to the ax equals to summation as r goes from 0 to infinity to a to the r x to the r over r factorial. This is the definition. We can see that x to the, if we apply phi to both sides, phi of e to the ax will give us the discrete version of e to the ax, which is equal to summation as r goes from 0 to infinity to a to the r x to the falling r divided by r factorial equals to summation r equals 0 to infinity a of r x choose r. This is very similar to the first equation here, the first theorem here of the binomial theorem here, but with one b replaced by 1, which we will get as a plus 1 to the x. This is the discrete version of e to the ax. What happens if we know we need phi of sine x? We can use the definition of the sine x as e to the ix and e to the negative ix divided by 2I. We can apply phi to both sides. When we apply phi to sine x, we get 1 over 2I multiplied by phi of e to the ix minus phi e to the negative ix. We will use what we derived before as e to the ax, phi of e to the ax equals to a plus 1 to the x, we can write it as follows. If we change this into the polar form instead of the Cartesian form, we will get these equations. If we take the square root of 2 to the x as a common factor, we will notice that this is precisely the sine of pi over 4 multiplied by x. So we have derived phi of sine x to be square root of 2 to the x sine of pi over 4 to multiplied by x.